Hi, it's Mr. Baker here. Today we're going to be looking at some circular motion examples. Okay, so today we're going to be looking at some centripetal forces and circular motion examples. And we're going to be looking at this question: why are some corners in racing tracks banked? So I'm going to just go through some different examples, and then I'm going to show you how to work it out, and then there'll be a problem that you can have maybe a go at doing as well. So let's have a look first at motion in a vertical circle. So here I've got an object that's going round and round in a circle. It's got its centripetal force going towards the centre of the circle. Let's have a look at that and analyse that a little bit further. So if an object is whirled in a vertical circle at a constant speed, then the resultant force is the centripetal force. For a given speed, the centripetal force is constant. The weight is going to stay constant and the tension in the string will vary. So at the side, the tension in the string, Ts, is going to equal mv squared over r. Okay, so that's going to be there, mv squared over r. We're just looking at that force there. At the top, the tension at the top is going to be plus the weight, mg, and that's going to equal mv squared over r. And the tension at the bottom, take away mg, which is the weight, and that's going to equal mv squared over r. So we've got three different situations here. If you look at the diagram, what's going on, the tension at the side is just going to be our centripetal force, because this force here, the weight is at right angles to it, so it doesn't matter. So it's just going to be that tension there. Here we've got the tension pulling down plus the weight down, and then here we've got the tension going to the middle, but the weight is going down. So this weight, mg, is going to stay constant all the way around as it's moving around, whichever way it's moving around. So the tension in the string is going to change as it moves around. So if you have a look at an example, so you might have an aeroplane doing a loop-the-loop. So you've got three different places here. So we'll have a look at a very specific situation here. A stunt plane does the loop at a constant speed. The radius of the loop is 200 meters and the mass of the plane is 9,100 kilograms. If the centripetal force is 89.0 kilonewtons, show that the speed of the plane at A is about 160 kilometers per hour. So if you want to pause the video and you can maybe use what we've just looked at to see if you can work that out. Otherwise, we'll just go through this one. And then maybe you can have a look at pausing the video and having a go at some of the ones in the future. So we said that at the side, the tension was going to be equal to mv squared over r. So that means our centripetal force is just going to be equal to mv squared over r. So here at A, the force at A is going to be equal to mv squared over r. And so we can work out that. So 89,000, we know that the centripetal force is 89.0 kilonewtons, 89,000. And the mass is 91,000 here, so we put m in here. V squared, that's what we're trying to find out. And we know that the radius is 200. So we work that out, put all of those numbers in, rearrange the equation, and we find that the velocity is 44.2 meters per second. And if we convert that into kilometers per hour, that's about 160 kilometers per hour. So there's 1,000 meters in a kilometer and 3,600 seconds in an hour. Okay, so that's an example that you might have to work out. Let's have a look at a different one. So we've got another example. We've got a car travelling over a humpback bridge here. A car travelling over a humpback bridge. At the top of the bridge, the force from the road on the car is R. We're going to call that the reaction force R. So R is upwards and is in the opposite direction to the weight, and the weight is going to be mg, the mass times the gravity. The resultant inward force is going to be the centripetal force, and so mg, which is going to be going down, take away r, which is the reaction force, which is going to be in the opposite direction to that, equals mv squared over r. So the weight, mg, is constant, so as v increases, the reaction force will decrease. When the reaction force r equals 0, the wheels are just about to leave the ground. The maximum speed at which this occurs is going to be mv squared over r take away mg. So we've got r as 0 in this case down here. So mv squared over r equals mg, and so we can work out v by using the square root of rg. So let's have a look at an example of this. So if you want to have a go at this, you can. A car of 1300 kilograms travels over a humpback bridge. The diameter of the curvature of the bridge is 30 meters. Draw a diagram of a car travelling over a humpback bridge. So that might be the first part of the question. The top speed the car can go before its wheels leave the ground is about 30 miles an hour. So the resultant inward force is going to be the centripetal force. So like I said, if you want to have a go at this, you might want to just pause the video and then have a go. Otherwise, I'm just going to go through it. So the resultant inward force is the centripetal force. So mg take away r equals mv squared over r. So when r equals 0, the wheels are just about to leave the ground. The maximum speed in kilometers an hour at which this occurs is going to be mv squared over r equals mg. So we can rearrange the equation. V equals the square root of rg. So we've got the radius is 15 meters because we said that the diameter is 30 meters for that bridge. G is gravity, which is 9.81 meters per second squared. So the velocity is 12.13 meters per second, which is about 43.67 kilometers per hour, which equals about 27 miles an hour or about 30 miles an hour. And that's what we had to show, that the top speed that it could go is about 30 miles an hour. Okay, so that's an example, another example there. Let's have a look at another one. So this is a pendulum, but it's being swung around like this. We call this kind of pendulum a conical pendulum because it's kind of sweeping out this cone shape, isn't it? So a conical pendulum like this will have these kinds of forces. The force acting on the mass are the tension in the thread and the weight. So you've got the tension in the thread going up there and the weight going down there. The tension is resolved into horizontal and vertical components. So vertically, the tension vertically is t cos theta equals mg. So that's t cos theta going up, and that's going to equal the weight. And horizontally, t sine theta is going to equal mv squared over r. So t sine theta is going to be this bit here, and that's going to equal the centripetal force, which is mv squared over r. So what we can do here, we've got a sine and a cos, so we can divide those together and we can get tan. Sine divided by cos is tan, isn't it? So tan theta is t sine theta over t cos theta, which in this case equals mv squared over r divided by mg. So that gives us tan theta equals v squared over gr. Okay, so we've divided through, and actually we don't need to worry about the mass in this case. So let's have a look at an example of a question that you might have. A mass of 50 grams is hung by a string and then forced to travel in a horizontal circles as shown. Draw the forces affecting the mass. So you've got the tension, which is going towards the point which is being hung by, and the weight, which is down there. Resolve the tension into its component forces. So that's another question. So you might have something like we've just seen. So the tension is resolved into horizontal and vertical components. What can you say about the value of t cos theta? So we've resolved into the horizontal component and the vertical component there. The horizontal component is t sine theta and the vertical component is t cos theta. And vertically, t cos theta equals mg. So what can we say about the value of t cos theta? The value of t cos theta is equal to the weight mg. If the angle between the string and the vertical is 30 degrees and the radius of the circle is 20 centimeters, what is the speed of the mass? So we don't know the tension, so we need to cancel it out. So horizontally we know that t sine theta equals mv squared over r. And so we can divide through like we did before. Tan theta equals t sine theta divided by t cos theta. So we're getting rid of the masses here and we're getting rid of the tensions. So that gives us tan theta equals v squared over gr. So tan theta equals v squared over gr. So tan 30 equals v squared over 9.81 times 0.2. So 30 was the angle here. G is 9.81, that's our gravitational field strength. and 0.2 is the radius. We had the radius in centimetres, so we've just converted that into metres. So we get, if we rearrange that, v is the square root of 9.81 times 0.2 times tan 30. So we get an answer of v equals 3.15 metres per second. So final example is the one where we had our question at the beginning about banking the road. On a bank track, the normal reaction and the friction both have a component towards the centre of the track. These combine to give the resultant centripetal force, allowing the car to go around the bend faster than if it wasn't banked. So here's a drawing of a car on a banked track. So have a look there, you can see that vertically, N, which is, we're calling the normal force, the force at right angles to the banked track, N times cos theta equals mg. So we've resolved vertically there. So we've looked at this component up here, and n cos theta equals mg. Or we could rearrange that, n equals mg over cos theta. So horizontally, n sine theta plus f cos theta is our centripetal force, which is mv squared over r. So we've got n here, so we're looking at this, we're looking at the horizontal, so n sine theta, in this case, is going this way. Then we've got force, the force down here, force times cos theta, that's also going in this direction, that's going to be our centripetal force. So if the road provided no friction, a car could still turn around a corner. The centripetal force where there is no friction is going to be n sine theta, seeing as this F is caused by friction. So we can substitute like this, n sine theta divided by n cos theta equals tan theta, and that equals v squared over rg, just by substituting those values in. Right, so this is what we should be able to do at the end of this lesson. You should be able to draw diagrams of examples showing resultant force. You can apply equations for circular motion, and you can do that in lots of different contexts. So our question was at the beginning, why are some corners in racing tracks banked? And that's to enable cars to travel around those corners faster, so that we have a component of the force acting towards the centre of the circle, that's coming from friction caused by gravity that's pulling that down. Right, so that has been all about centripetal motion examples, and I have been Mr. Baker, and I will see you next time. Thank you very much.